So what I want to talk about today are basically generative models for creating 3D objects. And so if you recall, the last lecture, we had to spend a little bit of time talking about like what even were the right representations for 3D objects, right? We could talk about voxel grids or point clouds or meshes or NeRFs. And so now we can kind of think about how do we extend ideas from 2D generative modeling to 3D generative modeling. So that's what we're going to talk about today. So 3D generative modeling. And so there are a lot of papers in this area, and we could kind of categorize them in various ways, right? So we could kind of build a grid that says, kind of on one axis, we have the representation, right? So I could have, you know, point cloud, mesh, voxel grid, NeRF. And on the other axis, I could have like VAE, GAN, diffusion model. And then kind of on top of that, I could have kind of like a checkbox that says, you know, is there, you know, text conditioning, basically. Like, could you type a prompt and get a response? And so kind of what I've chosen to do here is kind of proceed by kind of rows of this table, right? So kind of talking about different methods for given 3D representation. And then we'll talk a little about, you know, in the same breath as a given row, whether or not we're going to do text conditioning or not. And so, like I said, there are dozens of papers in this area, just like for any generative modeling thing. And so one thing to check out is that, for example, the first reading on this week's or today's lecture is this Deep Generative Models survey, right? So that's a good place to start if you want to learn more about kind of any of the stuff I talked about and kind of dig into all the references. And I've put in a dozen or so references that are, I think, are kind of like the critical ones in this area, most of which have just happened in the past like year or less, right? So a lot of stuff came out this year in 2023, and then a bunch of the key stuff also came out in 2022. So again, this field is moving fast. And then another place to look is awesome 3D generation. So this is kind of like the history. There used to be like a website called Awesome 3D Vision, Awesome this and that. So here, this is a great place to look for, you know, all sorts of papers and, you know, GitHub repos and so on in this area. So kind of a one-stop shop for 3D generation. Okay, so let's get to it. So let's talk first about, even though I didn't do this in the right order, so let's talk first about like voxel grids, right? So if you remember, voxel grids are kind of the most direct extension from 2D to 3D, right? And a lot of early work was done in this area. So, you know, straightforward extension from 2D. And so a good early example is this paper that, let's see, yeah, this Wu et al. NeRFs paper is a good example of a voxel grid paper. And so kind of how does that work? So basically, it's a pretty direct extension of GANs to voxel grids, right? The idea is that you have a latent. So for example, if I'm looking at this paper, this Wu et al. Paper, we could start with a latent, say like a 200-dimensional latent that is distributed as usual in kind of like normal 0, 1. We turn that via a 3D convolutional network into a cube that has a lot of channels but low resolution. And then we kind of keep on upsampling the size of the cube while decreasing the number of channels, ... until I get to the largest voxel grid. And this only has one channel, and it may be, for example, a 64 by 64 by 64 voxel grid, right? So this is like an all convolutional 3D network for the generator. And so this is, they use this for a GAN. They also combine this with a VAE encoder to kind of take advantage of 2D images as well. So they actually had something that was kind of like this. You know, 2D encoder, or you start with an image, you encode the image via a VAE that gives you a latent, You put the latent into a GAN, and then the GAN gives you the 3D voxel grid. And so you kind of train the whole thing from a database of 2D images of 3D shapes, basically. And so that's something where, again, we didn't talk about this so much last time, but one of the difficulties with generative modeling of 3D in general is that there isn't a lot of kind of like paired training data that you might see in the image world, right? So image world, we have ImageNet, we have other databases that have like literally, tens of millions of images. There really aren't that many 3D databases in the same way. And once you have to also pair those 3D data sets with text descriptions, you have even less, right? So here's a way of basically kind of learning from 2D images of 3D objects, which you can always create with a rendering program or by projection, right? And so initially, and you can do all the same stuff we talked about in the context of VAEs and GANs. You can do shape arithmetic and morphing and stuff like that. Generally, these early works were restricted to the 3D databases of object classes that existed. For some reason, you see a lot of information, or you see a lot of examples of like chairs and tables, which I guess were some of the early 3D databases that were out there. And then I'll show you some real examples in just a second. Another paper that came to mind is basically a paper by Mittal et al. This was CVPR 2022, which uses a VQ-VAE model on a voxel grid. So just to say that, you can apply a GAN to a voxel grid, you can apply a VAE to a voxel grid. It's all kind of more or less the same type of idea. Now, of course, once CLIP came on the scene, right? Remember, CLIP is the thing that allows us to associate language with images, right? And so then there are many papers that used CLIP as the basis for doing zero-shot 3D object generation, right? And so a key paper there was something called ClipForge. And for that, I do have a picture. So let's take a look here. Right, so here's a picture of ClipForge where you could, I don't know why this is cut off. Let me close right here. Yeah. So you could basically specify a simple text prompt, and it would make you this kind of chunky voxel grid result, right? And so the idea was that, again, mediated through language, you can start to generate 3D objects that kind of take advantage of text-to-image pairs instead of just text-to-shape pairs, right? So let me just kind of write some notes about how ClipForge works. So Sanghi et al., and this was just last year, CVPR 22, ClipForge. So the idea is that given a 3D scene, we can look at it from some given angle, create an image, and then describe that image with CLIP, and then say how similar that CLIP description is to a CLIP text prompt, right? So the idea is that the 2D picture of the 3D scene is what's kind of making all the magic happen, right? So the basic idea is that you have a kind of a autoencoder for the voxel part. So it's like, let's suppose I have a 32 by 32 by 32 3D shape. I learn via a VAE some sort of embedding, and then I also have a paired decoder that comes back to the voxel grid, right? Now, once I have this, so this is like step one. Step two is to train a conditional normalizing flow model. So you remember perhaps that normalizing flow was one of those little side algorithms we talked about along the way. But the idea is that once I have an object, I can make a bunch of 2D images of the 3D object. I can describe each of these things with the CLIP image encoder. That produces, some embedding C, and then I can use a flow model conditioned on the embedding of the 3D shape to kind of result in a Gaussian, right? So this is kind of like the forward part that takes the complicated distribution and turns it into a Gaussian. And then if I want to generate something, I kind of go the other way and say I start with a Gaussian. So if I want to generate something, I have a text prompt, which is something like, a picture of a blank. This is my text prompt. I use the clip text encoder to give me some C. I put this into my flow model, and the input to the flow model is the Gaussian. That gets turned back into an embedding, and then I can use my 3D decoder to get a voxel grid, right? And so it's kind of using a bunch of different things that we talked about throughout the class, right? You've got this idea of a VAE, the idea of clip, the idea of normalizing flow. And so this paper produced, as you can see back to here, some, pretty reasonable, oops, not you, here, some pretty reasonable results, right? So not only could you make like objects like, a boat or a table or something, you could even have some sort of like, qualifications, like a square table, a circular table, and so on, right? Of course, these voxels don't have any color associated with them, so we're going to go a little bit further than that, but this was kind of like early work, right? And then this was followed by a follow-on paper that they called Clip Sculptor that was even faster and even higher resolution. So the same group kind of went on to do something called Clip Sculptor. So followed by Clip Sculptor in CPR 23. Although I think Clip Forge is kind of like a cooler sounding algorithm. Okay, so again, voxel grids we talked about as kind of like straightforward extension. The next thing to talk about is point clouds. Okay, so we talked about before how point clouds are natively produced by lots of 3D scanning hardware, and so it makes sense to try to design generative models that can produce those kinds of things. So in the world of point clouds, the pioneering work was out of Stanford, if I recall correctly, Akliopoulos et al. In ICML 2018. And this was basically, a combination of a autoencoder plus a GAN to operate directly on raw point clouds. Now, this requires a little bit of thought. Remember that we talked about why point clouds are complicated is that, all I have to operate on is a kind of a unlabeled set of XYZ points that don't have any order associated with them, right? And any permutation of that XYZ set is actually the same point cloud, right? So we can't necessarily rely on this being point number 1, point number 2, and so on. So, for example, we need to design things, for example, comparing two point clouds. We need an algorithm that does so in a way that doesn't depend on the ordering of the points. And so just as a side note, we need things like, let's say permutation invariant comparison algorithms, like, for example, the chamfer distance is something that you'll see if you read point cloud papers. So if I'm trying to compare two point clouds, I have a distance between basically set 1 and set 2, which says so I over all of the x points in set 1, I find the closest point in set 2 in terms of Euclidean distance. And then similarly, I add up all of the points in set 2, find the closest distance in set 1, and again have this kind of thing. So this is the means by which two point clouds are compared. And also it's all differentiable, so we can still kind of do pushing this as a cost function back through the neural network. And so the basic idea in this original paper was, again, you train an autoencoder on a point cloud set. So kind of like you say, first I train an autoencoder where I have an input point cloud. For example, maybe it has 2048 points in the cloud. That goes into an encoder, which in the original implementation was a type of CNN. What you get out of that is a 128 dimensional latent. Then you have a decoder, which was a fully connected network. And then what comes out is a point cloud, right? So this is like your kind of vanilla autoencoder. And then the GAN operates on this latent space. I mean, they looked at it in a couple ways, as I recall, but they found out that it worked best if the GAN operated on Z. And so the idea was that we take noise as input to the generator. This was just a multi-layer perceptron. It produced this latent Z, and then I put this through the decoder I learned earlier to get a point cloud. So this, again, like I said, was probably one of the first works on point cloud models. And again, this was before all of the excitement about diffusion models, right? As soon as diffusion models came on the scene, then obviously everyone started to work on those, right? And the diffusion models were kind of cool because, just the way that noise in the image turns into the clear image, in 3D, it's kind of neat. You can imagine that you start with basically a noisy point cloud in 3D, and then those points just basically turn into the object, right? So it's like they harden up into the solid object. So it's kind of fun to think about this diffuse cloud of points turning into the object. It's kind of a different way of thinking about diffusion. And so it was from Zhao et al. In ICCV 2021. So, diffusion-based models. This was like Zhao et al. ICCV 21. So the idea is that you basically start with total 3D noise, and then I take a diffusion step. After that step, again, this is probably not the best drawing because everything looks like dots do, but I have a little bit more structure to my set of 3D points. I keep on taking steps, ... until the 3D, cloud is in the form of whatever this thing is. I don't know. It's a bug of some sort, right? Final model. Unfortunately, I don't have a video of the point clouds like diffusing into the object, but you can imagine how it would look. And so most recently, OpenAI released an algorithm called PointE, kind of as a continuation of their naming scheme of DALL-E. This is PointE. So this was OpenAI 2022. And so this was a pretty cool system that was able to generate point clouds that were not only point clouds, but they were also colored point clouds. So this generates colored point clouds based on text prompts. And again, kind of the nice thing, and I'll talk about how it works in just a second, is it's nice that you can make things that are not conditioned on existing classes, right? So this picture here, we're still kind of in the world of, cars and planes and tables, things that already have like kind of 3D model classes. But PointE, you could ask for, again, whatever you wanted, a chair in the shape of an avocado, and you could create it, right? And so you see here, again, these are clearly point clouds. You can actually see the boundaries of the points. The model is not like an airtight or a watertight mesh or anything like that, but it is resembling what we want. And so how does this work? So the idea is that, again, we're going to use something like CLIP, basically, using 2D pictures of the point cloud to mediate creating our result. So this is a, PointE is a diffusion model. using clip and glide. So if you don't remember, glide is kind of like the predecessor to DALL-E in some sense. And it uses a DALL-E-like structure. So the idea is you start with a text prompt. You use glide to generate a synthetic image. And this text-to-image generator is kind of specifically trained for images of 3D renderings, right? So it's not trained on your generic types of photographs. The idea is that they took a library of lots and lots of 3D objects, rendered them from different perspectives, and then used glide to do it. So this is like basically fine-tuned on 3D renders specifically. And then once I have the image, I can basically have a clip description as part of the vector. I have a time step, and then I have a list of RGB XYZ points, right? So this is like kind of like the points that I have at iteration t. And then I apply a diffusion model on the point cloud conditioned on the clip value and on the time step to produce, these things stay the same, and then I have my updated set of RGB XYZ points. And again, this diffusion thing is based on transformers, just like many things are. And so the idea is that I'm kind of using a diffusion model on the point cloud conditioned on the clip embedding and the time step. And it's pretty fast. So if everything goes according to plan, we should be able to do a quick demo here. So this is Pointy running downstairs. Wait, is this Pointy or is this Shapey? This is hard to see, so small. This is Pointy, right? Yes. I believe so. OK, so we can say, for example, you can't get as crazy with these prompts. I'm going to say a lemur wearing a scarf. Let's see how it does with this. And then I'm going to hit play. So you can see that the little progress bar is spinning around here. It shouldn't take us too long to get to a final result. I don't remember how many iterations it takes. Yeah, so now the point cloud is generated. It does a quick render. And then we should be able to see that point cloud. Let's see here. I guess it's over here. Penguin wearing a hat, lemur wearing a scarf. So open this up with a, well, I don't know how impressed I am by this picture. Let's try a different prompt, because maybe I was a little bit too aggressive with my clever prompt. Yeah, none of these prompts look very good. So how about let's be a little bit, let's say a happy clown. Let's see what happens there. I'm sorry, the text is so small on the screen. I should probably do something about that. But you can see the generation here is on the order of, under a minute, I would say. And then some of that generation is even just from the perspective of like rendering. So let's see a happy clown here. Whoa, I don't know what we're looking at here. All right, let's give Pointy one more try to prove itself here. How about something that it can't get wrong, like, no, not you, Edge. How about, let's forget all the adjectives. Let's just say a koala. How hard could this be? So one thing you can see, for example, is this is not like mid-journey level, ability, but the thing you're training it off with is the ability to do it extremely fast, right? So I'll show you some examples in just a few minutes where we can see these incredibly, detailed 3D models, but it takes those models like 45 minutes to create. So I can't do that in an interactive way during the class. All right, Pointy, this is your last chance to generate a model that will impress the class. Survey says, I don't think in any realm of possibility this would be a koala. I mean, it's certainly a 3D object, but it looks like it's been mutated by something or other. I'm not sure there's any difference between these two ways of looking at the koala. Now, here you can see at least the point cloud X, Y, Z points. All right. Let's just generate like a race car or something. I'll give it one more chance. I mean, with the way things are going at OpenAI, this software may not even exist next week. So, we're going to use it while we can get it. OK. Come on, Pointy, don't let me down. Race car. All right, this at least I think looks kind of like a race car. All right, it's got wheels, it's colored. All right, this looks more like a El Camino, but yes. So you can see proof of concept, right? And actually, I guess this is kind of like a mesh over the point cloud, but the source point cloud you can see is in fact a set of 3D points, right? And so kind of what's happening here is there's kind of like this coarse-defined generation of the mesh. So I think it starts with 1,024 points and then upsamples that to 4,096 points. And it works OK, right? You wouldn't use this in your game, but you can get something that's fairly fast. And this will only get faster in the future, right? Like we talked about last time, meshes are not the most natural representation for 3D generative models, just because unless you're using some sort of really fancy like graphical neural network, they're not really that well suited to the kinds of operations that we would typically do in a neural network. So I'll just say that meshes are less common for generative 3D. But one notable exception worth knowing about is called Get3D. This is from Gao et al. From last year's NeurIPS. And so this is a GAN-based method that kind of is inspired by StyleGAN that uses two random latents to control basically the shape and the texture of a mesh. And so let's just say it, GAN-based, kind of similar to StyleGAN type idea. We have a latent for shape and a latent for texture. And the mesh is represented by a kind of a fancy representation. We have a sign distance function on a deformable grid of tetrahedrons. And we talked last time very briefly about this triplane representation that they used as the kind of inherent 3D representation. Using that, they made some pretty good looking results. So these are some examples that came out of Get3D. So you can see they're kind of like, people, motorcycles, animals, and so on, right? And this looks pretty good. And so this, like I said, is kind of like an unusual way of doing it, but the results are pretty reasonable. So the paper is called Get3D. And then, of course, we move into the era of NeRF, right? So NeRF is what everyone thinks about these days when they think about 3D. This kind of like, weird way of thinking about a 3D object as specified by what you would see if you looked at it from a given angle and a different point, right? So the next innovation was kind of NeRFs. And so Of course, when NERF came out, it kind of changed the game in terms of how it represents scenes. But on the other hand, if we're thinking about how we're going to train these algorithms, there aren't a lot of NERFs to learn from, right? There's no like big NERF library or much less a database of like NERF scenes that are described by 3D. And so a lot of the NERF type stuff is generally creating a NERF from a text description, right? So we're generally creating or modifying a NERF based on text prompt. And again, kind of like mediated by images and language. So same kind of idea. Kind of what we're trying to do is we're trying to make a NERF such that projections of the NERF are consistent with the clip image descriptor and with the text descriptor, right? So at a high level, the idea is to learn a NERF so that its renderings have high similarity with a text prompt. And the kind of hidden assumption here is that the text prompt that you would call a rendering should basically be the same no matter what angle you look at the object at. So if I've got a koala wearing a hat, no matter what direction I look at it from, I could still describe it as a koala wearing a hat, right? And so the idea is that for each iteration of training, what I do is and so let me just say that, what am I describing here? So the key paper here was called Dream Fields. We talked about Deep Dream and what was the other one? Dream Fusion we're going to talk about, Dream Fields. So this was in last year's CVPR by a team from Google. And so again, the idea is that for each iteration of training, we kind of take our current NERF, and it's parameterized by some big, parameter vector theta, and we kind of randomly select a camera pose P, and then we render an image I of theta comma P from that pose. And then I want to minimize, basically, I look at the clip image encoding of the image I have, and then I dot product it with the clip text encoding of the caption or the prompt that I give it. And then there's also like some extra stuff, like there's a cost function to encourage that, there's a term to encourage transparency in the NERF volume. Meaning that, one of the problems with NERFs that you saw in the videos from last time is that sometimes you get these kind of like floaters in the periphery of the 3D volume that maybe you don't see them from certain angles, but from other angles you see there's like this crap floating around. And so one way of thinking about this also is that, suppose I took a bunch of pictures of a scene. What I could imagine is that the scene is composed of square pieces of cardboard that are kind of taped together in 3D space so that when you look from a given angle, you see the 3D scene, right? So you can imagine that I have a bunch of flat cards in front of the cameras that all the images would be consistent with that weird construction of cardboard, but not with a kind of a solid 3D object in the middle of the world, right? So the idea is to force the NERF to be shooting rays through empty space until they hit an object kind of in the middle of the space, right? To make it not think about 3D space in a way of that doesn't make human sense, right? And so this was pretty cool, and it makes pretty good images, right? So here's an example of dream field output. So again, you provide a text prompt. No, cannot play media. You can play the media. I know you can play the media if you try. Let me try this one more time here. So let me close this up and make. Sorry about this. Sometimes we have a clash with PowerPoint and no, not UNIRF. 3D, here we go. Okay, let's try this again. Come back to OBS. What's the problem here, OBS? Don't know why. All right, there's this, there's this, there's this. PowerPoint. Here. All right, sorry. We're doing it. For some reason. And of course, after this, probably the video is not going to play, but you never know. All right, let's try it now. Here we go. Now I can't play this media, but you can get the idea, right? So this is like a 3D object, and it doesn't look like a voxel grid or a mesh, right? Because this is like rendering the NERF. And you can do these kind of things like looking at this clear vase, right? Of course, you can't exactly see through the vase, but you kind of get this sense that this is an intricate object, right, that is created by the NERF. And so just to say that you can do, pretty nice, combinations of prompts, right? So you can say, a blank in the shape of another blank. But it is slow. Orders of magnitude slower than pointy, right? So I can't do an interactive demonstration of dream fusion for you, or dream fields for you. This was followed by another cool algorithm by many of the same people called dream fusion. This was in ICLR last year by Poole et al. And so the big difference between dream fusion and dream fields is that the clip piece is replaced by a kind of a different loss function. And it also uses a kind of a NERF variant where the old NERF, if you recall, parametrized things by looking at the radiance coming out of a point from a given angle. And that meant that the lighting was baked into the NERF, right? Instead, this NERF basically is parameterizing the color of the surface itself. So this is parameterizing surface color, which means that you can move the illumination around during training and then later during rendering. And so that makes the things that you generate a little bit more usable. If you're trying to put something into a game engine, for example, you don't want the lighting to be baked in from the start, right? And so this is basically, again, each of these NERFs is trained from scratch for a given object. So you can't really use what you generate for anything else. And again, you need a pretty powerful machine to do it. And this could take more than an hour to do, right? Even on this powerful machine. So again, something that's definitely not interactive. But the results are good, right? So let me show you, here, for example, are some dream fusion results. You can see it kind of does a swipe to show you the actual 3D. And so this doesn't have the prompts necessarily. You can imagine what they were, blue jay on a tray of macaroons, raccoon wizard, parrots playing chess, stuff like that, right? And so again, this is a kind of a neat algorithm. I don't know, Almog, did we try Dream Fusion on the computer in the lab? Did we get this to work? Or was this one of the ones that we never got to work? OK, I remember we did something that took like a long, long time, but I guess it wasn't this. So one thing you can see is that while the results are cool, they are also fairly low resolution. And so the next step was an algorithm called Magic 3D that was generally higher resolution. And also, they claimed twice as fast as Dream Fusion. So again, twice as fast in this case, meaning like 40 minutes.
Yeah, we did get
OK. So 5 hours for Dream Fusion is what we found out. So yeah, we never tried this one, though, Magic 3D, I don't think, right? And so one of the things that made this algorithm faster was that the original NERF paper uses as its core a multi-layer perceptron that is probably not the most efficient way to put the neural network together. So they use a multi-resolution diffusion model that was much more efficient computationally, although it still did take a while. It still wasn't very interactive. And finally, the last and probably most recent development here is called Shapey, right? So again, from the people that brought you Pointy, we also have Shapey, right? And so Shapey represents 3D using, you kind of have a choice of an implicit function, which could be a NERF, or it could be like a get3D type underlying mesh. And so here you can see that these models, they use some of the same prompts, and they get models that are clearly not point clouds, but are kind of like, images, right? And so what you do is you kind of like query the NERF to get the image. So OpenAI has a proprietary database of millions of text to 3D pairs that they use to train this model. And so let me just say in my written notes that what we're talking about now is Shapey, which just came out earlier this year. And so this combines a bunch of things, right? So it combines, representations, diffusion, latent diffusion, in a way that is computationally very fast. So basically, again, this is kind of like a speed-quality trade-off, right? So the results that you get from Dream Fusion are really cool, but they're not interactive, right? And so the Shapey should be interactive. So let's go back to the computer downstairs and see what we can do with Shapey here. So Shapey is over here. So I guess what we learned last time is not to get too fancy. So let's try, let's try a koala again. Let's try a koala wearing a hat. I mean, I need to be a little bit ambitious here. So you can see the progress bar is moving pretty fast here for Shapey. And then let's see what we get. So I guess we see it over here. Survey says, well, I see a hat. And I guess, are these the eyes of the koala? This koala has a massive nose. All right, well, let's maybe not get too ambitious again. This is my whole problem, is being too ambitious. Let's just start with the koala and see how we do with that. This is what we mean by the speed-quality trade-off. What happened? Uh-oh. Now it's not doing anything at all. Did I mess something up? Maybe yeah, I don't know why it didn't work. All right, well, you saw it work once. I don't know what happened after that. Almog, any ideas? Oh, I interrupted it while it was rendering, and now it's confused, right? All right, let's try it one more time. Well, if we restart the kernel, then it will. All right. So you say. Well, the demo never works when you want it to. But you saw something happen, right? And so I guess we can come back to this and see if this ever works. But Shapey, produces some decent results. And actually, if we go to the browser, you can see lots of examples on the Shapey website, which is here. I guess that maybe I should just be Googling Shapey here. I thought that there was like a nice project page for Shapey. Well, here you go. So these are some Shapey results, which are, again, a little bit chunky. And I guess that I was maybe too aggressive in asking for the koala wearing the hat. But, I think that apparently the 3D model that people always use is the chair that looks like an avocado. So, not bad, right? And so you could try using this at home and see how well you do with it. So basically, the other thing that I found was that Luma AI, who makes the NERF app that we were talking about, also has a alpha thing called Imagine 3D, which looks pretty good. Again, with the prompt and the 3D. And so let's try what this looks like over here in, I see that the Shapey woke up in my other browser, so we can come back to that. But let's look at, let's see, I think we do a Discord. Like Midjourney, this thing from Luma AI is called Genie. And so let's try here, a koala wearing a hat. Thinking. Close windows up while it's thinking. I guess actually we can see some other things while the koala is going, right? So here, cool hat, Roblox style, very cool dragon with a cowboy hat, hypercar. So just like Midjourney, you can just kind of scroll through and see like what kinds of prompts people are using. And these are much more simple prompts, except for this one, laser cut, whatever this thing is, right? How's my koala doing? Still thinking? No. And then I guess also it can generate some prompts. When I did this earlier, it was pretty fast. So I guess we can come back to this once it generates my koala. So so Shapey, also Luma AI's Imagine 3D, also known as Genie, is what we were just using. Oh, okay, I got my koala. So let's go back to Discord. That's all right. I think those are all pretty credible. And so again, if you're not waiting in the queue, I think that this, whatever is under the hood here, is comparable to Shapey or Pointy in terms of speed, right? And also it looks like a lot more higher detail than we can get out of Shapey, right? So again, I'm not sure how much actual information there is about what Luma AI is doing under the hood of this, but my guess it's also kind of like an implicit function-based NERFy type thing. So this is all kind of along the lines of just simply generating something from a prompt. And then, I'm not going to go into too much detail, but once we have the 3D representation, then we can try to do all sorts of kind of like editing or stylizing. And just in the past year or so, there have been a lot of very cool papers that have come out on kind of post-processing generated 3D images. So for example, one is called ClipNerf, right? So ClipNerf is kind of like saying I start with a source image and then I give it a prompt like make it an SUV, make it kind of go in the direction of SUV or go in the direction of sports car, right? And so we're modifying this. I don't remember what, obviously it's a NERF, right? So I was gonna say I don't remember what representation it is, but clearly we're changing the NERF according to a text prompt, right? So this is ClipNerf. Then there was a paper called Instruct 3D, which is pretty cool. So this dinosaur museum thing is a kind of typical NERF thing that was collected by somebody as a data set for real images. And so the original NERF is on the left, and then you can post-process the NERF to say, what if this was a Lego, make it out of Lego bricks, or what if this was painted by Picasso, right? And so you're changing the texture of the NERF according to the text prompt, right? Which again, you can imagine kind of comes down through kind of like a clip type description of like, can you now modify things to match up as well as possible with the text prompt? Then there's something called ARF. So ARF is like stylizing a NERF in the style of a given image prompt, right? So if you want to take your original NERF, we played this one, this is one of the original NERF pictures too, and turn it into something that is kind of like stylized by a sample painting, right? Then you can make this plant in the form of Starry Night. I especially like this playground one that's playing in the lower right. I think that's just really slick, right? So you can take this photorealistic NERF and turn it into this kind of artistically rendered texture, which I think is pretty slick. That came out just last year. And then this is work called Instruct NERF to NERF that just came out this year in ICCV, where you take a NERF, in this case this person, and then you apply a text prompt, and you can kind of immediately change it in, well, I don't know about immediately, I don't know how fast it works, but you can change it into different prompts of things that agree with the text. And so again, this is something that is really cutting edge. It's just come out in the past, the past few months. Some of this stuff I don't even think even has a, some of this stuff has GitHub repos, and some of this, the GitHub repos are even still coming, right? But it's amazing that it works so well. And so all this stuff is pretty fun to think about how quickly things have moved in this area. I mean, NERFs didn't exist 3 years ago, and now we're able to kind of make this kind of like editable 3D, representation. That's pretty cool. I like that one. Anyway, so yeah, so let me just write down, just kind of what I just talked about. So we talked about clip NERF, which was from CPR last year. We talked about instruct 3D to 3D. And so one thing that you'll see, this instruct blank to blank is kind of a common formalism in some of these papers, where you're basically saying, take the source thing, which is a 3D object, and turn it into another 3D object based on my instructions, right? So this was by Kamada et al. This year. I'm not even sure where this paper appeared. Then ARF was, again, recently in ECCV last year. And then Instruct NERF to NERF was also just recently. And so if you look at the web page for the class, we have links to these various things, right? So here's, like, for example, the ARF project page, where it takes a while to load up all the stuff, but I selected some of these just as examples. But you see they've got like a zillion examples on their page of kind of cool artistic NERFs. Many of which are like, this bulldozer is like a classical NERF example that has then been kind of like re-rendered by, all these things, right? So this is pretty cool. And the other one that I was showing you was Instruct NERF to NERF out of Berkeley. This is the video I was just showing. So yeah, for more information, take a look at the original project pages, and then you can kind of see more about how it all works. So homework 5, basically, before, let's just look at this. Whoa, freaky. So it's kind of idea of like, make him this or do that or turn him into that, is kind of like the prompting that you give to these systems. And so homework 5 is basically do something cool with NERF, right? So NERF it up. And so I'm curious to see what you come up with. One thing that we talked about last time was just you may have to be careful when you're planning your collection, because I want you to think about like things that are cool to take a picture or to make a 3D version of, right? So things that are kind of like transparent or shiny or have a lot of intricacy to them. You know, that is something that's, I think, more interesting than just taking a picture of like a teapot on your desk, right? So just keep in mind that the more complicated your scene is, that you may face the fact that your first part of the NERF, which is having to estimate where the cameras were that took the pictures, may stall out, right? So you may have to try a couple of things to see what works to get past that first step. But again, I think it'll be instructional to find out just like how well this stuff works when you try it on your own. All right, so any questions or comments about this 3D to 3D stuff? Yes?
I would ask if anybody's actually using NERF in industry, like game development or CGI.
Is anyone using NERF in industry? Well, that's a good question. So there are definitely ways of taking the NERF output and turning it into any of the point cloud, mesh, whatever, and using it for later, right? But I don't know of anything where people are like using NERF as a way of like modeling an environment in a game or something like that, right? Part of it is that no matter how good these look, they still do have kind of a flavor of being a little bit not low res, but like let's look at an example here. So like I'm not really sure what you do with this in a game, for example, right? Like how would you use it, right? So it's kind of fun. One thing that I like about the NERF results is the ability to kind of retarget the camera, right? So being able to kind of fly through a scene and see it from perspectives that you never saw it from before. Of course, I think they will suffer from angles that you never actually had a camera anywhere close to, right? So the NERF won't know what's going on behind my back if you ever took any pictures of anything but the front of me, right? So so I think that maybe one way of thinking about how it could be used is kind of like, you see these videos, you see these kind of like cinematic shots of like, the arrow that is fired through the, tiny ring of this swing set or something like that. You can imagine that you could collect data of the playground, right? And then you could re-render the point of view of the arrow going through the thing, right? So places where it might be infeasible to actually put a camera path due to the size that the camera would have to be or how fast it would have to be moving or something like that, there I could see some sort of value in re-rendering the NERF, right? But to my knowledge, it hasn't made it into like a film production or anything like that yet. Or to be honest, I'm not sure that any of this stuff necessarily has either. But it'll only get better, right? And of course, that's again what a lot of the actors' strike was about recently, was having control over what AI tools can do to a captured version of you, right? So you imagine that you had like Keanu Reeves, right? Make him blonde, make him cry, right? So you can imagine that, once you had a really high quality 3D version of you that could be then edited after the fact and maybe even animated, right? Then you could imagine what people are worried about, right? So I think that will probably be a new frontier in people worrying about what you could do with this, right? So one thing that we haven't shown here, which I know there has been some work on, is moving NERFs, right? There was a great example, and of course I probably can't find it on command, of something where the video was basically of a guy pouring, like mixing drinks in his kitchen, and somehow the NERF was moving around this scene in real time, it seemed, right? So it's like, I didn't quite remember how that scene was captured or generated, right? But imagine that you could move through these non-stationary scenes would be really cool. Or you could animate parts of the scene, right, that are individual, like you could animate the lips or something like that of a head that you had captured, right? So all that stuff I think is going to come down the pike, right? The other thing I would say is that, from what I know of visual effects and so on, like, the animation of, the quality of the 3D objects that you put into a movie, right, when you're rendering that movie at cinema size, right, you can't have a 3D object that isn't really photorealistic or sharp, right? And so I think that some of the stuff that's coming out of like, Dream Fusion and Dreamfields and so on, while it looks great, it's still not something that you could like put into a scene in a real movie and accept it as a generated 3D object, right? Not yet, but maybe soon, right? Like these objects don't have like really sharp square edges, right? They're kind of, lumpy and bumpy, and they're not like really parallel planes or anything like that. So there's still some ways to go in terms of maybe regularizing the NERF to create like really nice sharp objects, right? Like I don't think I've seen anything that really comes out looking that sharp. I guess the only exception would be that some of this Mesh 3D stuff does look a little bit on the sharper side, right? So like these objects look pretty good. Although if you look at the houses themselves are again kind of like lumpy bumpy, but you could imagine that if you needed to make like a crowd simulation or a scene with like a bunch of random animals, you know, in the background, that maybe this is kind of getting close to what would be good enough, right? Other question, yeah.
So is that just nerve force that can infer on unseen real object? For example, like find how you can predict whichever angle belongs to.
Right, so NERF cannot create unseen views of the object very well, right? So when you're synthesizing the NERF from the prompt, you're kind of sampling the views of the object. I think you're forced to sample, it's not a regular sampling, but you're definitely sampling all the way around the object, so there are no like weird things happening at the backside of the NERF, right? So I think there's some plan for when you pick the pose to sample at a given step, you make sure those poses are well distributed around the whole object so you don't have any like weird holes, right? Certainly when you're acquiring your own NERF, you could definitely have problems where you miss something and then you'll find out that something looks really weird from one side. And I'm expecting that when you guys are capturing your own NERFs, there'll probably be something you didn't remember and you'll find out that the NERF looks pretty strange from some perspective, right? Yeah. Okay, so that's 3D generation. I'm going to stop the recording.